Hey, is this Reed?
Yeah, this is Reed.
Well, I got some news for you.
So, Doc, what are my results?
Well, it seems the stent we implanted last week has become infected.
Is there any good solution?
Well, there are two. We can re-implant the stent and give you antibiotics, which you have to take 4 times a day for several weeks in hopes that the infection won't come back.
He always forgets his medicine.
Well, there is a second option. We can coat the stent in a new, innovative drug delivery method, microparticles.
That sounds really interesting. Can you tell me a little bit more about that?
Hi everyone, we're Team 25016, Microparticle Manufacturing Process Design. We're developing a cutting-edge microparticle making process to help patients like Reed. By refining medication delivery, we're making treatments more precise and effective. So why microparticles? Well, unfortunately, patients like Reed are all too common. Take this statistic. 1 in 30 hospital patients have at least one healthcare-associated infection. That's over 1 million patients every year. Microparticles provide a great solution to more than just this complication. A microparticle-based drug delivery system would remove the need for invasive forms of entry, reducing risk of infection and adding the benefit of highly targeted delivery. Today, we'll talk about how we're developing these treatments and give you some insight into our technology and our aim to improve patient care. Microparticle manufacturing today is largely undeveloped, lacking specificity to produce particles with consistent release mechanics. In the pharmaceutical space, that's a big deal. 1 gram versus 500 milligrams of a powerful drug can make a huge difference. So there's a clear need to develop a process refining the microparticle manufacturing. Research shows 2 key characteristics with significant impact on particle release mechanics: surface morphology and particle diameter. Drug delivery applications dictate our microparticles to be in the 5 to 50 micron range. For morphology, we use design space exploration principles and mapping extreme design conditions to determine an approach of creating 2 very different morphologies, smooth and islandy. So specifically, our primary goal is to characterize a process to create smooth and islandy microparticles in a targeted size range.
We have broken down our microparticle creation process into 4 main subsystems. This is 1, composition, 2, manufacturing, 3, characterization, and 4, diagram. Composition has to do with our chemicals and their respective ratios. Manufacturing has to do with the machinery that we use with those chemicals. Analysis has to do with how we characterize our final microparticle batch. And finally, diagram is where we reflect our results and experimental factors, and that is the final deliverable that we give to our customer.
To develop our initial setup, we studied a wide range of research papers covering topics like microfluidics, biomedical materials, and chemical properties. This research helped us understand the flow rates, choose appropriate solvents and drugs, and determine the type of microchip we're going to use. We selected acetone as our solvent due to its safety and chose 3 different drug types for testing. The double T-junction microchip stood out as the best option for our design, and we built our first ever setup around it. Our setup used 1 syringe pump for the active phase and 2 for the continuous phase. These were then pumped into the microchip to form microparticles, which were then collected in a beaker of continuous phase and stirred using an overhead stirrer.
The first problem with our initial system is that pressure within the chip was causing our connections to leak. So to try and solve this, we tested different connections and flow rates, and we ended up with a chip that has screw-on connectors to prevent the leaking. All of our experiments were only producing clogs within the chip. So to solve this, we first used a simplified system using only water colored by food dye to visualize those interactions within the chip. We also tried adjusting our flow rates and lowering the concentrations of both of our phases. In the end, none of these solutions worked, so we end up switching our solvent from acetone to DCM, which is immiscible in water to create that oil and water emulsion. We also switched over to glass syringe pumps that have a more consistent output, and we used a chip with larger channels. At this point, we were producing consistently smooth microparticles, but they were above our size range, so we worked on lowering our flow rate ratio to get those smaller microparticles.
Now going over our overall process to create microparticles. There are 2 key phases involved. First is the active phase. The active phase is made up of a solvent, drug, and hydrophobic polymer. The continuous phase is made up of DI water and a hydrophilic polymer. These 2 phases are placed in glass syringes and a syringe pump, connected with tubing to a microfluidic chip. The continuous phase flows at a faster rate than the active phase, so when in the chip, the continuous phase cleaves the active phase, creating bubbles. So due to the hydrophobic and hydrophilic tendencies of the two phases, they won't mix together and the bubbles will remain intact. Flowing through to the output where the overhead stirrer is, the microparticles are stirred so that the solvent has time to evaporate. Once the solvent has evaporated, our microparticles have solidified their structure and are ready for filtering. When filtering, we first use a larger filter and funnel to separate any larger particles from the smaller ones. We then use a vacuum filtration setup and a smaller filter to get out the rest of the particles and wash them with DI water. We then put these into tubes and freeze them for lyophilization. Once dried, they're ready for SEM analysis.
Safety and standards are core to the procedure. We carefully follow standards like ISO 13485, which guides quality management for biomedical processes. Our process is fully documented, controlled, and traceable. Safe chemical lab practices are integrated as well. PPE is used at all times, along with fume hood.
We've successfully completed over a dozen distinct batches of microparticles. Let's take one of our more recent ones. This batch had a mean diameter of 40.23 microns with a standard deviation of 6.8 microns. What made this batch more successful than previous batches? Well, we changed two main factors. The first factor was altering the ratio of the continuous and active flow rates. And the second thing we altered was changing our solvent from DCM to ethyl acetate. That was for a batch of smooth microparticles. Well, how did we create islandy microparticles? We changed three main things. The first thing we changed was decreasing the amount of continuous phase in the output beaker. The second thing was changing the drug type, and the third thing was increasing the drug to PLG ratio overall.
For verification for our main size and morphology requirements, we used SEM to get high-resolution images. To start, we found the morphologies present within our images and then found the frequency of each of those to get our prevalence. This was typically around 95%, which gave us a margin of 45%. After that, we found the size of the particles within our images, and for our better batches, the average size was around 40 microns or less, and their standard deviation was around 20%.
We will be delivering a technical data package, process and design specifications, and a comprehensive visual diagram to BD in Engineering 498. The visual diagram consists of experimental factors and the resulting microparticle characteristics. The user can pick a microparticle with a desired size and morphology and determine the experimental factors that create it. They can also choose a set of experimental factors and see what the resulting size and morphology of the microparticle will be. We hope that microparticles can be the future of drug delivery systems, and they can continue to be improved by evaluating their biocompatibility, testing their degradation profile, and their long-term stability.
The team executed a safe and reproducible procedure for producing microparticles. We successfully characterized different microparticle morphologies in a targeted size range. These improvements were made with invaluable support from a variety of places. We specifically want to thank our sponsors, who greatly aided us in this process and provided us with everything needed for project success. We also want to thank the College of Engineering, who afforded us the opportunity to work on an exciting and impactful project. Their support are making it possible for medication delivery to transform in the very near future.